Is PPT visible? Full screen?
Yes.
Hello? Is it visible in full
Yes, sir.
screen? Okay, thank you.
Yes, sir.
Yes.
So, okay, thank you. So today's topic is a voltage regulator again, as the unit is voltage regulator. So topic, it is a voltage regulator using IC LM723. It is 14 pin IC and has functional blocks inside that we'll see in this lecture. So the three terminal regulator discussed earlier have following limitations. The limitation is, first one is no short circuit protection available in previous ICs that we have seen, and second is output is fixed, either positive or negative. These limitations have been covered or overcome using IC LM723 voltage regulator, which can be adjusted over wide range of both positive and negative voltage regulator. You can see into the diagram, it is a pin configuration of general purpose IC LM723. You can see it is available in plastic pack, first one, and it is available in metallic pack. Plastic pack is also called, we know that it is dual inline package, where you can see total 14 terminals are there, out of which terminal number 1, terminal number 14 is not connected. Terminal number 2 is current limit, 3 is current sense, 4 is inverting input, means it of course there is an op amp inside, 5 is non-inverting input, then 6 is V reference, which will provide you the reference voltage from Zener. 7 is minus supply if required, else it may be grounded. Pin number 8 is also not connected. Pin number 9 is Zener voltage. Pin number 10 is the output. Pin number 11 is VC. VC is nothing but controlled voltage. Here we can connect unregulated power supply. Yes, anybody has question? Pin number 12 is positive power supply. This is also unregulated power supply. So supply and unregulated power supply means, that is 11 and 12 is always, you can see, shorted together, because 12 is the power supply to the IC and 11 is the input, unregulated input to the regulator circuit. So these two terminal are always shorted, and pin number 13 is frequency compensation, to remove some frequency component or noise from the output, which is always connected to pin number 4 through one capacitor of 100 picofarad recommended by the manufacturer. Another package is metallic pack. You can see here pin number 1, this is pin number 1, is current sense, pin number 2 is inverting input, pin number 3 is non-inverting input, 4 is reference voltage, 5 is minus supply, either use minus supply or maybe grounded if you are not using negative supply, 6 is output, 7 is control voltage, 8 is plus supply to the IC, and these two will be always shorted, 7 and 8. 9 is frequency compensation, recommended 100 picofarad capacitor between this frequency compensation and the inverting input, and pin number 10 is current limit. So these are two packages available. Again, theory question will not be say there in the examination. One more thing I would like to highlight is that till the time, means in previous all three papers, there is no question on IC 723. So there are, say, major chances to have design question on IC 723 this time. Another is, we are moving into the IC now. So here is a regulator IC functional blocks. So in that, actually we have two separate sections inside this IC. Section 1 has what, a reference amplifier, which is also, we can say, which will provide you fixed reference voltage V reference derived from the constant current source and the Zener diode Vz. If the Zener diode is driven by a constant current source, we know it provides very constant voltage across it, and which is used as a reference voltage here. Another section, section 2, has an error amplifier which will minimize the error between output and the fluctuation. So this is error amplifier. Another one is a series pass transistor, which is Q1 shown here, where VC is a control voltage, is nothing but unregulated power supply is to be connected to this VC, and output is generated across emitter of this transistor Q1. So this is series pass transistor. We know the major parts of the voltage regulator, without which voltage regulator cannot be possible, is the reference. So reference generator will generate reference. Another is the error amplifier. So this is error amplifier to minimize the difference between input and unregulated output. Third one is the series pass transistor, which is here in the form of Q1. And fourth one that we know is a feedback, and here inside IC there is no feedback. Externally we will be connecting component to provide feedback, that is part of the a fraction of the output is taken back into the input of the error amplifier. And one additional feature to this IC is this transistor Q2, which is current limit and current sense transistor. This transistor Q2 can sense what is the current passing through the output terminal, and accordingly it can control whatever we required. Obviously there will be some external component, current limiting resistance RSC, connected to this transistor, and accordingly it will limit the current. So current limit is one of the additional feature or functionality of this IC. So these are the two sections of the IC LM723. So section 1 only provides fixed reference voltage of V reference of 7.15 volt. In certain book it is approximated to 7 volt. In several design it is taken 7 volt, but will in every numerical will take it 7.15 volt. And second section is consisting of error amplifier, series pass transistor as I mentioned, and current limit transistor. These are the three, say, functions in section 2, and they are separated to each other, and by connecting external component, obviously feedback component and current limiting component, we can configure this IC into low voltage regulator and high voltage regulator. So specification of this IC is input voltage maximum can be handled is 40 volt, not more than 40 volt is possible. Then output voltage adjustable from 2 volt to 37 volt. So output voltage can be obtained from 2 volt to 37 volt, out of which if you move for the range 2 volt to 7 volt, it is configured as low voltage regulator, and 7 volt to 37 volt it is configured as high voltage regulator. Maximum output current of this IC is 150 milliampere. That's why this IC is also called low current IC. Output current cannot be say output current without bypass transistor, but with the help of bypass transistor we can boost this current up to 10 ampere by adding one bypass transistor externally, and this can be used either a linear or switching regulator, both can be possible using IC723. Next PPT, LM723 voltage regulator can be configured into two positive voltage regulators. One is first mode or configuration, we can say it is low voltage regulator. Range will be 2 volt to 7 volt. Second is high voltage regulator. Range is 7 volt to 37 volt. So of course, in what fashion the functional blocks which are inside the IC are connected together will decide which mode of operation. Moving to the next PPT, first mode of operation we'll see here is low voltage regulator. The range is 2 volt to 7 volt. If you want output is equal to 2 volt, 3 volt, 5 volt, up to 7 volt, you can achieve this by choosing proper value of external component. You can see the unregulated power supply, which is DC, fluctuating power supply, is connected to the control voltage at pin number 11. Supply to the IC is pin number 12, which is V plus. They are shorted together. As I mentioned, these two terminals are always shorted together. Then V reference we get at V reference, we get 7.15 volt due to Zener and constant current source. It is available at 6 terminal. From that, we have connected one resistance R1 into the non-inverting terminal, that is pin number 5 of the IC, and one resistance R2 is connected into non-inverting terminal towards ground. 0.1 microfarad capacitor is recommended by the manufacturer to reduce the ripples, and there is no say role of 0.1 microfarad capacitor into the output voltage calculation. Then negative supply, that is pin number 7, is directly grounded as we are moving to the positive voltage regulator. So negative supply is not needed, so it is grounded. 100 picofarad capacitor is connected between pin number 13 and 4 to remove high frequency ripples. So this is also recommended by the manufacturer, and there is no role of this capacitor into the output voltage calculation. And output is taken across pin number 10, which is connected to, of course, load, and from the output one feedback resistance R3 is connected into the inverting terminal of error amplifier. So this all connections is the low voltage regulator configuration. We'll have functional block diagram of this. If design problem comes into the exam, functional block diagram is not required to draw, but this block schematic is required. Whatever is there on your mobile right now, this is mandate to draw into the examination while designing. But whatever I am moving to, this one, this functional block diagram is only for understanding purpose, no need to draw into the examination. So we'll connect all the component which we discussed on earlier PPT, this one, on functional block diagram. We'll join it together. You can see here, I'll use highlighter. V reference में से एक resistance लगाया था, that is R1 into the non-inverting terminal. You can see here R1 is into non-inverting terminal and V reference. There is another resistance connected in parallel to the capacitance 0.1 microfarad towards ground from non-inverting terminal. You can see these two components are connected. One another capacitor of 100 picofarad is connected between frequency component is nothing but output of error amplifier and inverting terminal, that is pin number 4. Then this pin number 12, that is plus V, and VC. VC is nothing but collector of transistor Q1, which is series pass transistor. They are shorted together, you can see here, and unregulated power supply is directly connected to these two terminals. And output, that is nothing but emitter of the series pass transistor Q1, is connected to the load. And one more component, you can see from the output we have connected resistance R3, and that R3 is connected into the inverting terminal of an IC. So this is the complete functional block of low voltage regulator IC. Now let's see what happened here. Now as it is an amplifier, error amplifier, I'll erase the screen. So here you can see what is this. This is an error amplifier, which is operational amplifier. Considering this operational amplifier is an ideal one, then what is the differential voltage? Differential voltage is nothing but voltage between non-inverting terminal and inverting terminal. Ideally, the differential voltage is equal to 0. If inverting differential voltage is equal to 0, that means non-inverting terminal and inverting terminal will have similar voltage. Both will have similar voltage. Let's see what is non-inverting terminal voltage, which is here. In the above diagram, the voltage at non-inverting terminal of an error amplifier due to the voltage divider pair, that is R1 and R2, can be calculated like. So we can see here V reference is connected to R1, but here is the voltage divider pair due to R2 and R1. So non-inverting terminal voltage can be calculated as R2, because non-inverting terminal voltage with respect to ground is nothing but voltage across R2. So R2 upon R1 plus R2 multiply applied voltage is nothing but V reference here, which is generated by reference generator. So non-inverting terminal voltage is V reference into R2 by R1 plus R2. Moving here to the next PPD, you can see the difference between non-inverting terminal and output. Output is what? You can see output is directly connected through one resistance R3 to the inverting terminal. And what we said right now, inverting and non-inverting terminal जो है, their difference will be equal to 0, means they both will be at similar potential. So ultimately what we can see, inverting terminal is also at similar potential like non-inverting terminal, so that differential voltage, that is V non-inverting V minus V inverting, will be equal to 0. So the difference between V non-inverting and output, which is directly fed back to the inverting terminal through resistance R3 to the error amplifier, the output of an error amplifier drives the pass transistor Q1 to minimize the difference between non-inverting terminal and inverting terminal of an error amplifier. So whatever the voltage available here at non-inverting terminal and voltage available at this output, due to this error amplifier action, it will try to minimize the error between these 2 points, and whenever it is exactly equal, then the series pass transistor Q1 will be at certain conduction stage and your output will remain constant. Moving to the next PPT here, therefore you can write an equation. As I said, non-inverting terminal and inverting terminal is at same potential. That's why I may write that output voltage, which is nothing but here, this one connected through R3, output voltage is equal to V non-inverting, which is equal to V reference into R2 upon R1 plus R2. So these two resistances R1 and R2 decides what will be the output voltage. What is value of R3, which is not mentioned on the PPT? R3 will be parallel combination of R1 and R2. In this way you can have value of R3. Since we know that what is V reference voltage? V reference voltage is the reference voltage which is coming from the reference generator section and which is fixed, which is 7.15 volt. It is not fluctuating, it is fixed, because your Zener diode is driven by constant current source, so it will not fluctuate its voltage, it will be constant. Therefore, in low voltage configuration, formula is V0 is equal to 1.75 volt multiplied by R2 by R1 plus R2. Nothing but your output voltage is decided by two components, those are R1 and R2 connected here into the circuit. Again, I am repeating, functional block diagram is not necessary while designing into the examination. Theory question, if theory question is asked, probability is less, but if theory question is asked, then it is required, else it is not required. Now we will have one numerical. Before that, I will come back to you. Is there any question from your end till the time? What we have seen packages of IC723, its configuration, low voltage regulator, its block schematic and functional block diagram by connecting R1, R2 and R3. Any question, any queries? Because I'm moving to the numerical based on whatever we learned till now. Okay, so we'll again move to the PPT. Is it visible to you? Numerical one?
Yes, sir.
Okay, thank you. Numerical one, it is based on low voltage regulator IC723. You have to focus on numericals in this, say, subject. Design a voltage regulator using IC723 to get an output voltage of 3 volt. What is output voltage given? Output voltage given is 3 volt. We know 3 volt is within the range of 2 volt to 7 volt because circuit diagram will not be provided into the examination. So from this 3 volt, we have seen that it is within the range of 2 to 7 volt. Therefore, IC is to be configured into low voltage regulator, whatever we have seen earlier. So I am used low voltage regulator configuration, that is V in is connected to pin number 12 and 11. From V reference to non-inverting terminal connected one resistance R1. From non-inverting terminal to ground connected two component, that is R2 and 0.1 microfarad resistance, sorry, capacitor. Minus supply is grounded directly. Then 100 picofarad capacitance is connected into inverting and the compensation terminal. Then output, we have connected load, and from output into the inverting terminal we have connected R3, which is feedback resistor, and we know that R3 is alone, there is no another resistance along with R3, so there will not be any sampling to the output. Output is directly connected through resistance R3 into the inverting terminal. So complete output is taken into the feedback, considered into the feedback. So moving to the design here, because only one formula and only problem is how to select resistance value R1 and R2. So given is V0 is 3 volt within the range of 2 to 7. So low voltage regulator configuration is used. Output formula V0 is equal to V reference into R2 upon R1 plus R2. That is 7.15 into R2 upon R1 plus R2. The voltage across R2 is 3 volt. Let's move to the previous PPT so that we'll see how the voltage across R2 is 3 volt. Now, what is the output voltage required? The output voltage required is, we may use functional block diagram or block schematic. The output voltage required is 3 volt, means at this point the voltage is 3 volt. What is voltage at terminal 4 or inverting terminal? This will be also 3 volt. What error amplifier will do? Error amplifier will try to minimize the difference between inverting voltage and non-inverting voltage. So we can say that voltage at non-inverting terminal is also 3 volt. Therefore, non-inverting terminal voltage with respect to ground is 3 volt. Nothing but voltage across resistance R2 is 3 volt. So this is how it is mentioned here on this PPT. The voltage across resistance R2 is 3 volt. Therefore, value of R2 will be 3 volt divided by quiescent current of the IC IQ. It is referred as IQ. So it is 3 volt divided by 1 milliampere. 1 milliampere is the IQ, value of IQ, if you see the data sheet of IC723. It is to be fixed, okay? No one can assume this current. This is 1 milliampere, it is given into the data sheet. So 3 volt divided by 1 milliampere will provide you the value of R2 3 kilo ohm. Put this 3 kilo ohm into above equation. So we get output voltage 3 volt equal to 7.15 volt. In place of R2 I kept 3 kilo ohm and calculated value of R1, that is 4.15 kilo ohm. And value of R3 can be calculated equals to parallel combination of R1 and R2, which will be approximately near to the value of R2. So you can calculate value of R3 at your end. So this is how the voltage regulator is designed. If I use value of R2 3 kilo ohm and value of R1 4.15 kilo ohm, then with this configuration, this IC will provide you fixed output of 3 volt configured as low voltage regulator. Moving to the another configuration of the IC, that is high voltage regulator using IC LM723. High voltage regulator configuration is the range 7 to 37 volt. Maximum input can be connected 40 volt to this IC as per specification. You can see any of the configuration is there. Still the unregulated power supply V in is connected to supply terminal of the IC, that is 12, and the VC collector terminal of series pass transistor, that is nothing but input, that is 11 number terminal. They are shorted together and unregulated power supply is connected. Load is connected into the output terminal, that doesn't change again because output terminal is pin number 10 towards ground. But you can see small changes are there. One more thing as it is, that is 100 picofarad is connected into the frequency compensation terminal and pin number 4, that is inverting terminal, to remove high frequency component from the output. But you can, and minus supply as it is not required is directly connected to the ground, which is pin number 7 towards the ground. The change in the high voltage regulator, you can see the V reference which is generated by the reference generator at pin number 6 is directly connected through one resistance R3 to the non-inverting terminal of an error amplifier. And resistance R2 and R1 in voltage divider, say, configuration is sampling the output voltage, and sampled output voltage is connected to the inverting terminal pin number 4. So this is the high voltage regulator configuration. You can see the difference between low voltage and high voltage. There is huge difference. So here, using this component on functional block diagram, so you can see here the functional block diagram. V reference pin number 6 is directly connected to the non-inverting terminal by one resistance R3. So if somebody is asking you what is voltage at V reference, of course that is known to you. That is nothing but 7.15 volt, which is reference voltage fixed due to this Zener and constant current source. And if somebody asks you what is voltage at non-inverting terminal, non-inverting terminal's voltage will be also similar to V reference because it is directly connected through one resistance R3. There is no another resistance to say decrease this voltage. Sample nahi kiya hai usse. So directly connected through R3 means non-inverting terminal voltage is also 7.15 volt. Coming to the operation of transistor Q1, in what region the Q1 is operating? We know there are three operating regions of the transistor. One is cutoff, another is saturation, and another is active. This Q1 is not in cutoff because if there is cutoff, there will not be connection between unregulated and regulated output. Output will be 0. So this transistor never be in cutoff. This transistor never be in saturation. Saturation means across the transistor voltage is approximately equal to 0 and all the voltage coming from unregulated power supply will be available at the load. So it will not work like voltage regulator. So the transistor Q1 is in active mode. It is in on state. It is in active mode. Active mode is what? It varies its current IC. Accordingly, the voltage across collector and emitter varies, that is known as VCE. So whatever is the fluctuation into the input will be absorbed by transistor Q1 as we have seen at the start of unit number 1 in basic regulator circuit. So as I said, this transistor is in on state. That means the base terminal and the emitter terminal is shorted together as it is passing current through from base to emitter. It is shorted together. What type of, so in what configuration the transistor is? It is an emitter follower. That also we have seen in very first lecture of this unit, because base has an input from error amplifier, and output is at emitter, so it is emitter follower. I'll erase the screen. So this terminal, base terminal of Q1 and emitter terminal of Q1 is at similar potential because Q1 is working like an emitter follower. So let's see the relation between output of error amplifier. Output of an error amplifier is connected through the base emitter junction of this transistor, and there is resistance R1 and it is going into the inverting terminal. Let's have one more diagram here. I'll draw the op amp here. This is your op amp, say error amplifier. This is plus terminal. This is minus terminal. In the minus terminal, we have one resistance connected, which is R1 into the output. This one we have seen, because from the output to inverting terminal current is flowing. That means there is short circuit and it is connected through one resistance R1. So I may say that this R1 is the feedback resistance, and another one is the R2, and R2 is connected. Where R2 is connected? R2 is connected in the output and the ground. And what about non-inverting terminal? Non-inverting terminal is fed by one voltage, which is called V reference. I will write VR through resistance R3. So looking at this diagram, R3 से V reference non-inverting terminal में लगा है. Inverting terminal and output में we have resistance R1, and output and ground we have resistance R2. This is nothing but it is the non-inverting mode of operation of this operational amplifier. I'll repeat it. V reference is connected through R3 to the non-inverting terminal, means it is 7.15 volt connected to non-inverting terminal. Resistance R1 is acting like feedback resistance between output of an amplifier, error amplifier, and the inverting terminal, and output of amplifier and the ground has R2. So it is like non-inverting mode of operation. Therefore, what will be the non-inverting gain? It is written on the PPT. Look at this. The non-inverting terminal is connected directly to the V reference. The error amplifier operates in non-inverting amplifier mode. Therefore, the voltage gain of this error amplifier is AV, which is equal to 1 plus R1 by R2. If you remember what is voltage gain of non-inverting amplifier, it is 1 plus RF upon R1. But here in feedback there is R1 and in input we have R2. That's why voltage gain is 1 plus R1 upon R2. This is the voltage gain of this error amplifier. Moving to the next stage. As we have seen, this V reference is directly connected to the non-inverting terminal, will act as input voltage to the non-inverting mode of operation. So the output of this configuration will be output is equal to V reference, which is 7.15 volt. In certain book it is directly taken 7 volt, multiplied by 1 plus R1 upon R2 is nothing but gain of this error amplifier. So this formula will provide you required output by choosing proper value of R1 and R2. Again, I'd like to mention here, value of R3 will be parallel combination of R1 and R2. So this is all related to theory of high voltage regulator configuration. One thing I'd like to mention, this Q2 current limit and current sense transistor we have not used in low voltage as well as high voltage configuration yet. We'll see it later on, current limiting technique. We are just focusing on how to configure IC into low voltage regulator and high voltage regulator. We have seen what is low voltage regulator and also had one design numerical. Now we'll see the design numerical on high voltage regulator. Circuit diagram will be like this, as we have seen, block schematic. High voltage regulator using 723. Design a regulator using 723 to get output voltage 28 volt. So given is output voltage 28 volt, it is within the range of 7 to 37 volt. Therefore, IC has to be configured into the high voltage regulator. So you can see the high voltage regulator configuration, unregulated power supply connected to pin number 11 and 12. Then reference terminal 6 is connected to the non-inverting terminal number 5 through resistance R3. Output pin number 10 is connected to the load. From the output there is feedback resistance for sampling this output R1 and R2 towards ground. Middle terminal of R1 and R2 is connected to pin number 4, which is inverting. 100 picofarad is connected into the compensation and inverting, and negative supply is directly grounded as we don't need negative value of the output. Solution to this, as we mentioned, it is within range 7 to 37. So we'll go for high voltage regulator. Formula for high voltage regulator is 7.15 volt multiplied by non-inverting gain, that is 1 plus R1 by R2. The voltage across R2 is 7.15 volt. We'll move back and we'll see how the voltage across R2 is 7.15 volt. I'll move to the functional block diagram. So here I'm interested in looking at resistance R2, and I want voltage across resistance R2, which is connected into the output and the ground. So here we know that the voltage connected to non-inverting terminal is 7.15 volt, which is V reference voltage. And you can see one resistance is directly connected to the inverting terminal through resistance R1. So these two will try to minimize the difference. Thereby this terminal will have voltage 7.15 and will be the voltage across R2 with respect to ground. Therefore, the voltage across R2 is considered 7.15 volt. So voltage across R2 7.15 volt divided by IQ, where IQ is 1 milliampere from the data sheet of IC723. Dividing 7.15 volt divided by 1 milliampere, the resistance value will be 7.15 kilo ohm. Putting this into the above equation, we may have value of R1. So output 28 volt, then V reference 7.15 multiplied by 1 plus R1 upon 7.15 kilo ohm. So R1 comes 20.85 kilo ohm. So by choosing value of R1 20.85 kilo ohm and R2 7.15 kilo ohm, this IC will be configured to output is equal to 28 volt. And this 28 volt output get after this configuration will get value of R3. As I mentioned, value of R3 is the parallel combination of R1 and R2. There is one correction. This R2 is to be connected not here into the functional diagram. It is to be connected here into the inverting terminal and the ground. So this is R2. Please make correction. I'll upload the corrected copy on the Teams. It is an inverting terminal and the ground. We can see the functional block diagram. R2, I'll erase the ink first. You can see R2 is connected into the inverting terminal and the ground. In previous functional block diagram, it is by mistake, it is connected into the output and the ground. So here, by choosing these two value of resistances, we can have 28 volt at the output, and R3 will be parallel combination of R1 and R2. Now next topic, any query related to this? Yes. Anybody has any query? Because we are moving to the next topic. Yes, Bhagyashree Agrawal, you raised hand.
Sir, the value of hello.
Yes, value of
Sir, the value of R1 and R2 we found. Then what about the value of R3?
R3 will be the parallel combination of R1 and R2.
That is 1 upon R1 plus 1 upon R2.
Yes, obviously.
Okay, sir. Thank you.
Yes, parallel value. In earlier example also, in low voltage regulator also, R3 value is always R1 parallel to R2. Any other query?
Sir. No, sir.
Okay, okay. So I'm moving to the next topic is the current limit. So here, as we know, the output current of this IC is 150 milliampere only, and still suppose certain load requires very low current, say 25 milliampere or 50 milliampere or 100 milliampere, that is nothing but less than 150 milliampere, then we may have use of transistor Q2, which is inbuilt in this IC, which is referred as current limiting transistor. And now we'll see the use of this. Now here, current limit protection circuit, how it is used. We know unregulated power supply Vin is connected to what? Series pass transistor collector. That's why it is called VC. Then output is at emitter, and after this output, in earlier example, we have connected this output directly to the load, but I am connecting now one resistance called RSC, current limit resistor, current sense resistance here. Of course, if the current is passing through the load current will pass into the current sense resistance RSC also, and will develop voltage across it in this way. And this voltage we will refer, it is V sense. And that voltage is directly connected to the current sensing transistor Q2. You can see the base of current sensing transistor Q2. I will highlight the complete transistor here. Q2, which is referred as current limit terminal, is connected to one of the terminal of RSC. This CL, current limit terminal of Q2, is connected to one of the terminal of RSC, and another terminal called current sense, which is nothing but emitter of current limit transistor Q2, is connected to another terminal of RSC. You can see what is this? This is type of NPN transistor, and into the base and emitter we have connected RSC. If current passes into the load, same current will pass through RSC, will develop V sense across it, and that V sense is directly connected into the base and emitter terminal of transistor Q2. So it is obvious, if this voltage is less than 0.7 volt, transistor Q2 will be in off state. And if transistor Q2 will be in off state, I will erase the ink here. If transistor Q2 is in off state, then obviously current will only pass through the load and transistor Q1 and RSC. But if this load current is more and Vsense is greater than VBE on of this transistor Q2, then transistor Q2 will be in on state. If it is VBE on is always considered 1 volt, else 0.7 पे भी transistor on हो जाता है, but during design we consider Vsense or VBE on of this transistor is 1 volt. Sorry, 0.65 volt, because 0.65 volt is a Vsense. 0.65 के ऊपर अगर voltage गया means 0.7 वगैरह, so transistor will become on. So if it is on, then what will happen? ये जो error amplifier है which is driving transistor Q1, and suddenly due to increase in Vsense, this Q2 is on, some of the current will pass through collector emitter junction of transistor Q2. From where this current is coming? Obviously, this will reduce the base current of the transistor Q1. एरर एम्पलीफायर से जो करंट जा रहा था बेस में ट्रांजिस्टर Q1 के, वो करंट कम हो गया बिकॉज ट्रांजिस्टर Q1 is functioning, it is in on state, and if this current is less, obviously load current will be less, because load current is nothing but collector current of Q1. So automatically load current will get controlled. If load current is trying to increase, it will increase the voltage Vsense across resistance RSC. Due to that, transistor Q2 will be in on state, will bypass current, or we'll say sink the current from base of the transistor Q1, and as the base current is less or reduced, collector current of transistor Q1 has to be reduced, as the collector current is beta times of base current. Beta is constant, which is amplification factor of the Q1. So in this way, your voltage remains constant. At particular current limit, it remains constant. But as this current limit is increased, automatically transistor Q2 will turn on and current will be limited to whatever is the value decided by value of resistance RSC, which is current limiting resistance. So the earlier circuit, we have no protection. If the load demands more current, example under short circuit condition, the IC will try to provide at a constant output voltage and getting hot all the time. This may burn the IC. Therefore, it is provided with current limit facility can be utilized by connecting very small value of RSC, which can be designed by the formula. We'll see the formula across current limit and current sense terminal. So here we know that after passing certain particular limit of current, Vsense is greater than 0.7 or 0.65 volt, and transistor Q2 comes into the picture and will restrict its current to certain limit. Therefore, choice of RSC is very important. So the current limit I limit set by connecting an external resistance RSC between the current limit and current sense terminal. Current limit also connected to the output terminal of the IC, that is V0, and current sense is connected to the load. You can see current sense is connected to the load, current limit is connected to the output of the IC. The load current produces a small voltage drop across resistance RSC, which is called Vsense. Therefore, I limit will be having very simple formula, Ohm's law, Vsense divided by RSC. So Vsense is always 0.65 divided by RSC. Therefore, I limit will be 0.65 divided by RSC. If you wanted to calculate value of RSC at 50 milliampere, it will be RSC is equal to 0.65 divided by I limit. So 0.65 divided by 50 milliampere, it comes around 13 or 12 ohm. Putting 12 ohm resistance in place of RSC, it won't allow IC to provide more than 50 milliampere to the load. One of the example, numerical, maybe asked for 2-3 marks, at max 4 marks. Numerical is current limit circuit पे. Design a current limit circuit for IC723 to pass 60 milliampere current to the load here. Only 60 milliampere. So circuit diagram is like this. What is I limit is equal to V sense by RSC is equal to 0.65 divided by RSC. Therefore, RSC current sense resistor will be V sense divided by I limit. V sense is 0.65 always, and I limit it is given 60 milliampere only. So 0.65 divided by I limit 60 milliampere. It provide you value 10.83 ohm. So around 11 ohm resistance, 10.83 ohm resistance. If you connect here in this network, then this IC will not allow to pass current more than 60 milliampere. Less than 60 milliampere is possible, but more than 60 milliampere क्या होगा? If more than 60 milliampere, say current demand by load is increased to say 100 milliampere. So due to that 100 milliampere into 10 ohm around, so it will provide you around 1 volt across RSC. Due to that 1 volt transistor Q2 will be in on state, and initially whatever is the current passing into the base of transistor Q1 by an error amplifier, some of the current will be withdrawal or sunk by transistor Q2. Thereby the current base current of Q1 reduces. As the base current of Q1 reduces, collector current of Q1 also reduces, and collector current of Q1 is nothing but the load current IL. So in this way the current will be say reduced to 60 milliampere and kept there. Any question? Any question from your side? I think I shall stop here because I have further numericals as well in the same PPT, but due to time limit, we'll stop here, and later on we'll see low voltage regulator along with current limit circuit, high voltage regulator along with current limit circuit, and if load demands more than 150 milliampere, that is a rated current of the IC, how to use bypass transistor externally to boost current up to approximate 10 ampere. That also we'll see in the next lecture. Till the time, if you have any query, I'll wait for 1 minute, else I will end this lecture. I'll wait for 1 or 2 minutes. I'll stop sharing my screen. If you have question, I'll again share my screen. Waiting for your reply. If okay, if there is no queries from your side, thank you very much. We'll see the further part into the next lecture.